Hello and welcome back. Let's talk about surface integrals of vector fields. So, these are very similar to line integrals of vector fields, except we know what surface integrals look like now. So it's just basically a mix between those two. So it's denoted by this. The surface integral of our vector field f producted with our small segment in the vector of surface. Very strange, very unintuitive. Well, what this actually equals is the double integral over s of f dot n ds. But what's n? Well, n is the normal vector to the surface S. And so that's why we have our vector ds, because we need to know the angle that our vector field is entering our surface S. And if you remember dot products from linear algebra, it can tell you how much of the vector is similar to the other vector. And that's exactly why we're using a dot product here. But we still don't know what this actually means. Well, to find the unit normal vector, we need to use this formula. The formula involves the parametrization of our surface there it is. We take both of the partial derivatives, just like we did with regular surface integrals, and then we cross product them, just like we did with normal surface integrals, except this time we will be getting a vector, as we know. And so the reason this is called the normal vector is, you may recall from maybe physics you learned this in, that a vector, say b, can be represented by its magnitude times the normal vector b. And so if we want to solve for our normal vector, we have our regular vector up here divided by the magnitude of its vector down here. It's just this time we are talking about it entering in both directions into the surface integral. Now don't stress too much about understanding what I just said there. You should just stress about really understanding how to plug things into this formula. So let's derive an even easier equation, because we still want to evaluate this surface integral, which is still quite the lengthy task, unless we simplify something here. Well, we remember that the surface integral of a function, a scalar function, with respect to a small segment in the surface, is equal to the double integral over our region D of our function of our parametrization, and that would be not dot producted with, just times by the magnitude of the cross product of the partial derivatives of both of our parametric equations. So, what does this mean? Well, if we let this right here equal this right here, what we will notice is that if we bring this into here, we bring our normal vector and the equation for our normal vector into where the normal vector belongs, these two will cancel. And so what we will be left with is the double integral over d of our vector field represented in terms of our parametric equation dot producted with the cross products of our parametric equation's partial derivatives with respect to area, of course. And so this right here is the same as this, except a lot easier to solve. I think this marker doesn't want to teach you guys this as much as I do, so I'll be grabbing another one. We're working a lot here, guys. We're going to need a lot of markers. But let's hop into an example. First, let's rewrite this so that we do not forget the equation. Jeez, this marker's almost not as good. What is up with this? There we go. Just had to get warmed up. Okay. Let's evaluate this, and let's let some things equal some things. Let's say our vector function, our vector field, is just x, y, z. Very simple vector field. And our surface is y equals x plus z, where, like in past videos, I have just taken the square from 0 to 1. So let's figure some things out. Well, our r of, in this case, x and z is just going to be x plus z, z. Because we have an explicit function of x and z. So we can just plug that in for y. Okay, let's find the partial derivative of r with respect to x. This is going to be 1, 1, 0. And the partial derivative of r with respect to z is going to be 0, 1, 1. You could calculate the cross product of these, but I will just give you the answer. I believe it is -1, -1, and 1. Nope. 1, -1, and 1. Okay. Well, let's dot product these with our function f in terms of x and z. So our vector field in terms of our parametric equations of x and z is equal to, well, x equals x, y is x plus z, and z is z. Dot producted with this, we will get x minus z plus z. Now you'll notice this actually equals 0. So that means we have the double integral over d of 0 with respect to area, and this, of course, is just going to equal 0. But what does this mean? Well, at the start of the video, I told you guys that the vector field, or the surface integral of a vector field, can be thought of as how much of that vector field is going through the surface. Now, in fields like engineering, we would call this the flux of this field. And when the flux of a field through a surface is 0, it means that just as much vector field as is entering is also leaving. So vector fields such as magnetic fields will always have to follow this principle, because as we know from magnetic fields, if we have a magnet, our magnetic fields will always create closed loops, meaning that if we took any point here, there would be just as much coming into this point as is coming out of the point. So that is surface integrals of vector fields, otherwise known as flux of the vector field through a surface S. I hope this helped you as much as was needed. Thank you for watching, and I hope to see you when we talk more in depth about these.